Okay, what I would like to do now is state and prove Lebesgue dominated convergence theorem. I actually done this a little differently in the past, and I think the way I'm going to do it now is by far the most efficient way to do it. And besides that, um, you actually prove something a little bit more powerful than what typically Lebesgue dominated convergence theorem states. In particular, will prove L1 convergence, the Lebesgue-Donnelly convergence theorem. You can go to the videos on LP spaces, see what that means. Okay, so let's Lebesgue-Donnelly convergence theorem. So let's say, as always, E is measurable. Let's say this is a function, and suppose each Fn is measurable, and we have pointwise convergence almost everywhere on. So this is a theorem about interchanging limits and integrals. So we know, obviously, this is not nearly enough to do that. Um, the key thing here is that there is an integrable dominating. Suppose there exists G non-negative that's integrable on E. So the integral over E is finite, where each Fn is dominated by G for almost every X in E. If this is true, then we can interchange limits and now, of course, this here, I didn't suppose F is measurable, but this here implies, of course, F is measurable. All right, so, and as usual, you can be a little more general. Yeah, you could be a little more general than assuming complex valued on all of E. So remember, I'll do this in blue. So what this is saying is F is U plus I V for U and V being real valued on E. You can relax that to be uh so one thing I forgot to do. Uh say something. F is integrable. E follows very easily from this here. It is underlined. Um, but yeah, so you can relax this a bit. And you can assume that U and V are real valued almost everywhere. So they can spit out plus or minus infinity on a set of measure zero. Um, but not a huge, not a deep relaxation. All right, so before I prove it, maybe in the corner here, um, I'll state some facts here. that are pretty easy from 511. I don't know if you really ever use them other besides here. Easy homework. If each xn is real valued and x is real, or if each xn is real, we have a sequence of real numbers and x is real, then 1, not very surprising. I can pull out the x because it's a constant. Guess we really should have bounded below for this. And 2, this is very easy from the fact that the infimum of minus a set is minus the supremum of the set. Just by the way inequalities and minuses behave. Very, very easy. But crucial to the proof is that limit of minus xn is minus lim sup of. Okay, so now we can begin the proof. Big Don made converts. Okay, excising. So do the usual excising set of measure 0. We can assume yeah, we can assume particularly Fn goes to F on E. And this holds on all of so fine. All right, so first it's easy to prove that F is integrable. Very easy from Fatou's lemma. Basically all you do, well, as I mentioned, we have measurability because it's a pointwise, almost everywhere limit of measurable functions. Well, so because modulus f is the limit of the f modulus fn's, we also have modulus f. Well, we also have and this is the lim because limits converge to the limit. Limit exists and does. E. So just use Fatou's lemma. Uh, all right, well, each one of these is less than or equal to G. So this is less than or equal to integral G is. So actually, this argument, if you think about it, proves it's not part of the proof here, but we have essentially proved the following proposition, which is interesting unto itself. Yeah, each and measurable, um, let's say integrable rather. Let's call this C. Let's say the soup and equals 1 to infinity. Um, yeah, sorry. So I want pointwise convergence. Pointwise everywhere on E. And let's assume this is true, then we proved it already by Fatou's lemma. You get so is F. F is also integrable, and this is less than C. Right? Does this equals the lim inf? Fatou's lemma says less than or equal to the lim inf of the integral. That's clearly less than or equal. And not important for the proof, but definitely something to keep back in mind. Um, all right, so that takes care of that. So the last kind of claim before we actually essentially prove, get to the main arguments is it's enough to show, this might be obvious, but enough to show that this integral is pretty funky looking Fn. So meter. And this is very easy. Why? Well, just easy, 511 stuff, basic analysis. This is true if and only if, well, this here equals 0, which of course equals so really absolute value here, modulus value. Um, yeah, and obviously this is true if this limit is 0. Just because, well, obviously, this is less than or equal to this. All right, so yeah. So our task is to prove this. And yeah, so we're proving clearly something stronger than what we really have to prove. But besides that, I think it's actually easier just to work with this. rather than to directly try and prove, uh, yeah, rather than try and directly prove this, I think it's easier to prove this here. Okay, how do we do this? Very clever use of Fetuzla. It's a very, very nice idea that you use very, very, very often. So, how does it work? Well, I somehow need, well, first of all, we're going to fact show that lim soup uh, of this equals 0. That's what we're really going to show. And that's good enough because blue, well, clearly each f, let's say n minus f less than or equal to soup equal to n. This is trivial. And so if the lim soup goes to 0, then take limits of both sides. So let's call the star here. Yeah, so if this is true, then this is trivial stuff. So worth it to even mention, but it can't hurt again. Yeah, this is less than or equal to the lim soup. That's the lim soup. Squeeze it in here, never ever a good idea. Anyway. Right, we're assuming this is true. All right. So actually what we'll prove is that the lim soup is less than or equal to 0. Well, we only have non-negative terms, so the lim soup has got to be bigger or equal to 0. Um, so so that means the lim soup is going to be all right, so yeah, well, the thing is with Fatou's lemma is Fatou's lemma deals with the lim inf. So how do we go from lim inf to lim soup? We use 2. Somehow 1 is going to help us do that. So yeah, how do we do that? And I'd love to know who came up with this idea. Maybe it's Lebesgue. I don't know. I should ask ChatGPT and see what wisdom it imparts on me. I'm kidding. I actually like using ChatGPT. I just use the free version. Right. So what we do is you don't have to explicitly write this, but I'm going to set up a function that Fatou's lemma applies to. Well, let me make a note first so that's a little clearer. For each x and e, this is less than or equal to fn of x plus f of x And remember, this is, it looks like mustard. Well, G dominates these on E, so both of these are less than or equal to G, so it's 2G of X. So if Fn of X is bring this to the right-hand side, you get something non-negative. I claim that basically using Fatou's lemma, we're done. Also, Fn goes to F, so well, this part goes to 0, so this converges to G of X on E. All right, so yeah, let's use Fatou's lemma and hope for the best. We will get it. All right, so 2 times the integral of G is going to be equal to, well, this here. So this is the Fatou's lemma. So this is just this fact here, what I have. This here implies this trivially. This is Fatou's lemma. All right, so I just want to remind you of what this is. G of X minus this absolute value, modulus. So yeah, I can use fact 1. So my G of X, or rather, the integral of G of X would be like my X, so my X. Um, so yeah, first let me do this. Do this here. Let me make this a little bigger. Now, I'm doing here. So write it like this, plus minus uh Fn minus F. Guess it's weird without the X's. All right, so yeah. So you can take like 2 times integral of g to be your x. So this is going to be equal to, and this is kind of neat because have we can cancel 2 times integral of g from both sides, in particular because it's finite. We're subtracting a finite number from both sides. That's our assumption that our dominator is integrable. I believe I wrote that. I don't know. Yeah, there exists G integrable. Um, right. So now I'll basically erase it in a second. Plus limit minus this. But remember, we can pull this out here, and this becomes lim soup. That's the second fact. All right. Let's do that right now. Pull the minus out. And then this becomes a lim soup. And I claim that's it. We're done. So let me get rid of this. Get distracting this point. All right, so let's do green, I guess, or dark blue. So maybe before I do it, this is what I'll do. So we have 2 times integral of g is less than or equal to this here. That's the key things. So I'm going to cancel both of these from well, both from the inequality, so subtract off 2 times integral of g, and we literally get, like literally get 0 is less than or equal to minus lim sup. So often when you do like an argument like this, you might get like the lim sup is non-negative, which doesn't really help you often. If you're dealing with non-negative terms, that literally says nothing. But miraculously, this is saying the lim sup is less than or equal to 0. I'm just adding the lim sup to both sides, or minusing both sides. And again, the only way a lim sup can be less than or equal to 0, it can't be negative because we're dealing with non-negative stuff. The integrand is non-negative. That implies, finally, I'll just do that. Okay, yeah, so we're finally done. All right. Yeah, so a few comments, a few um very easy applications, maybe an example first. Um So we've done this example of what could go wrong if you don't have a dominator. But I think it's a good example. Let's say E is 0 to 1. And this is typically how you would actually prove that there is no dominator. You show that the conclusion of the dominant convergence theorem is false. The dominant convergence theorem is not false. It's a fine and dandy proof. So it proves that you can never find a dominator. So let's say Fn is any power bigger than 1 or any power bigger or equal to 1 works. Characteristic function 0, 1 over n x. So graph is obvious. Squared. Hole here. This is 1 over n. Of course, the area under this rectangle here is just going to be n, for each n. It's going to be obvious. Oops. So this limit here is infinity. The limit function here, of course, is 0. So this is 0. 0 is not equals infinity, so it's going wrong. The conclusion is that there's no dominator. No dominator exists. No integrable dominator. For the sequence F. Right. All right. So maybe an easy example. Yeah, trying to think of. Well, let me do kind of a really nice application of so we just made maybe one comment here. Exclusion. Yeah, exclusional big dominant convergence theorem fails. So and so what I want to next prove is kind of a subtle point of integration on the with the Riemann integral, and that's defining kind of being careful with improper integration. So what we're saying here, and you can prove basically the same thing when you're integrating a non-negative function using monotone convergence theorem. I will leave for you to state and prove such theorems, basically the same thing. Let's say this illustrates a very common skill you need to learn and master, which is kind of using dominant convergence theorem in times and places when you don't think it's relevant. Let's say this is integrable. for any real sequences, UN and VN, where these limits are infinity, we have basically this integral can be given I can basically state a version of this for any infinite interval. Let's just stick with the real line. All the damn. Yeah, so this is saying I can think of this integral as an improper integral, and I don't care how I approach plus or minus infinity. I get the same answer. By infinity, I mean plus infinity. So UN could even be like n, and Vn could be e to the n. So Vn would be going to infinity much faster than UN. Doesn't matter. As long as we're integrable, then yeah, it doesn't matter how we approach in plus or minus infinity. All right, and the proof, very, very, very easy. I could also state this kind of like it's a little kind of awkward if you want to state it as a limit, because what I'm really saying is it's like two limits. I'm saying I can approach infinity much slower or faster than I'm approaching minus infinity. Anyway, totally put it like this. So the trick is to set Fn of x to be this characteristic function. Of x. So trivially for each x, get pointwise convergence. Again, if you really want to, you can assume that the real and imaginary part of f is only real valued almost everywhere. So you can excise a set of measure 0. So you have convergence, pointwise convergence almost everywhere. And as often is the case, we have a trivial denominator here, and that's just absolute value of f of x. So by the Lebesgue-Dahme convergence theorem, equal to the following. Well, this, because Fn is just integrating, basically Fn is f, but with the characteristic function. To n, Vn, f. All right, and in that next video, there's a lot more applications of the Lebesgue-Dahme convergence theorem. Very, very, very useful thing. In particular, we're going to study the Fourier transform by means of the Lebesgue-Dahme convergence theorem, and prove that when integrating integrable complex value functions, the integral also behaves like Lebesgue measure. So kind of weird. It's like a complex valued measure, but it's fine. It still behaves like Lebesgue. All right, so long. Take care.